our gear to uh, the learning-based methods for computer visions, right? In the past 5, 6 lecture, we have been discussing about the conventional or traditional based methods for computer visions to perform some sort of basic image processing so that we can further use it for some kind of tasks in computer visions like edge detections, perform features detections, perform matchings, image stitching, something like that. Now we are going to switch to a learning-based method for the computer visions. So here today we are going to start with machine learning for classifications, specifically the image classifications. All right, so that's what we are going to talk about today. So today we will start the learning-based method with a classical machine learning classifier, which is KNN and linear classifier. So we will start building from this classical methods, and then we'll further going into a more advanced classifier or methods to perform the computer vision task later on in the class, right? Let's first talk about the intelligence and learning definition first. So because now we are going to start working on what we call a learning-based methods, right? So that's a learning-based method. So before we dive into the learning-based methods, I think many of you may have heard of the word artificial intelligence and machine learning. So there's the word intelligence and learning. So what's the difference? What are the similarity between the two? What exactly the definitions of intelligence and learning, right? So intelligence is nothing but we can look at the mental capability overall that is makes us as a humans that is capable of to reason, to solve the problems, and to learn from the experience. So that's what we call intelligence, right? But learning is more like a process, right? Learning is more like a process of acquiring new or improving the existing skill, abilities, and knowledge from experience, right? So that's the difference between intelligence and learning, right? So intelligence it is the mental capabilities, so which involve the ability to reason, right, to solve the problems and learn from the experience. So that's what we call intelligence. But learning is more like a process. Learning is a process, not a capability. It is a process that we can acquiring or improving our existing skill, abilities, and knowledge from the experience. So that's the difference between learnings and the intelligence. Okay. So just a brief quick overview to introduce those words. So now let's talk about the first classical machine learning models. We can see models, which is the nearest neighbors, right? So in this class, we are mainly focused on image classifications, all right? Which means that we are giving some sort of image, and then we want a machines or a models to classify whether the objects within the image or the image as a whole belong to which class. So that's what we call image classifications, all right? So for the image classification, we assign an image, all right? We assign an image to a known class based on the objects present in the image. So that's what we want to do. So, and we expect the models to output the SI image to one of the fixed set of categories, right? For example, we have a models that that is capable of predicting how many, 2, 4, 7 classes. So we expect that if we give it an input image, it will be able to assign the labels or assign the class or the categories to the image within this 7 category of the image. So that's the image classifier. So if I input a dog image, the image that has a dog inside that image. So I expect that the models should tell me that this image belong to the dog categories. So that's what we expect, right? So that's the image classifications. So we as a human, right? We as a human, when we look at this image, we can some sort of interpret the semantic meanings within this image. So we as a human, what we see is we see a dog wearing a Merry Christmas cap, and then has a small Christmas tree with a fan at the back. So that's what the semantic we can interpret, and then we can extract from these informations for this image. But for the computers, for the machines, what it see is just the array of numbers or arrays of pixel intensity. So that's what it sees. So this is what we call a semantic gap between humans and the machine. All right. So that's the semantic gap, right? So that's a problem when we are working with the image classifications. So as I mentioned in our first class, that when we are working with computer visions applications, so these are the challenges that we have to face within the computer vision task. For example, we have the illumination variations. So if the brightness of the image change, that would probably change the information that we can extract, or even a viewpoint variations. If we capture the image from different angle, it would convey different meanings, and also the intra-class variations, and as well as the occlusions. So, and also the scale variations, deformations, background cluster. These are the challenges that if we are working within the computer visions area, these are the challenges that we will face, and then we have to some sort of solve this problem. For example, in this background cluster image, so we probably wouldn't be able to. We sometimes, as a human, we wouldn't be able to detect an object within this image, right? So, for example, the one that down below here, if we don't pay a close attention, we don't even think that there's a dog within this image, right? So, but it is actually there's a dog inside this rock, all right? So even though we as a human, we sometimes like detect some of the object with this challenge, all right? So for the image classifiers, for image classifications, for the classifier, what we basically doing is like we have some sort of functions that receive the image as an input, and then what it's trying to do is trying to figure out some sort of features or some sort of characteristic within that image, and then trying to come up with the answer, whether what is the class label of this image. All right. So sometimes there's no obvious way that we can hard code this algorithm to recognize a cat or a dog or some other classes, right? So for example, what you typically do with a traditional computer visions techniques or image processing technique that we have learned so far, we probably could try, for example, if we have the image of the cat, we would probably try to find the edges, and then after that we would probably try to find the corners from the edges, and then we would come up with some sort of set of criteria that if this consists of multiple corners around the ear, and then multiple corners around the face, something like that. So you have to write the rule-based methods to figure out what kind of object that look like a cat. So what kind of features the cat should look like. So you have to manually figure out those some sort of rules, right? So sometimes if there's no obvious way that we can write such a kind of rules that can generalize for every classes, or even though just single class. If we are changing the viewpoint of taking this cat image, our rules would probably not be able to recognize this image as a cat, because we cannot write all the rules that can captures or that can generalize for all viewpoint, for all objects, or for all classes. All right. So that's the basic problems in traditional methods for objects or image classifications. All right. So that's why it's bring us to the classifier that we call a data-driven approach. So for data-driven approach, there are basically three steps that we need to do. So first, we need to collect a data set of images plus a label. So to do a data-driven approach classifier, we have to have the many images along with its label. Okay. And then we will need to train the classifier, right? We probably need to train classifier, have some functions that receive the image along with its labels, and then trying to extract some patterns from the image, and then come up with the predicted labels. And then we also might have to write another functions to perform a predictions. After training the models, we might have some functions to perform to give us a predicted label from unseen images, right? So that's how we can construct a data-driven classifiers. So basically, in machine learning areas for computer vision, there are many data set that has been constructed. As I mentioned in our first lecture, that collecting a data set is one of the core engine that push the boundary of machine learning or deep learning area. Because without this data set, I think we wouldn't go this much far as we are here today. So the very first and the most very simple data set that has been collected, and then it is widely used in the community of machine learning for computer vision or deep learning for computer vision, is the MNIST dataset, in which it is a black and white image of a digit from 0 to 9. So it has 10 classes. And this image is just very low resolutions. It's just 28 by 28 grayscale images. And in this dataset, there are 50,000 training images and 10,000 testing image. Okay. And the next data set would be CIFAR-10, right? So CIFAR-10, it has like 10 classes as well, but across different objects, not just digits, but it's ranging from like airplane, automobile, birds, cat, something like that. So it has roughly the same number of training images, like 50,000 images, but 5,000 per classes, and 10,000 testing images, and 1,000 per classes. And it has just a little bit higher resolutions, like 32 by 32, but it is a color image, RGB images, which means that it has 3 channels, right? So that's the CIFAR-10. And also CIFAR-10 can probably have like they keep adding the data set to like this should be CIFAR-100, right? So they're just extending the number of classes from 10 to 100 classes Yeah, so they add more classes and then make the data set just bigger, not bigger in terms of the number of images, but bigger in terms of the number of classes. Okay. And the one that is making that make the most contributions to the machine learning or deep learning community is ImageNet, right? It has over 1,000 classes, and then it has over 1.3 million training images, like splitting into training, validation, and testing, right? And they're also providing some like matrices to measure the performance of different models, like for example top 5 accuracy, and then so this ImageNet has been widely used for the computer visions and deep learning for computer visions for many years, but nowadays it is still in use as the benchmarks data set as well. So now we have been discussing about the data set, which is required for machine learning models, right? So now let's discuss about our first classifier, that is a nearest neighbors image classifier. So the nearest neighbor image classifier, it is nothing but what you're doing, or what the model is doing. It just memorize everything, right? It just memorize all the data and the label. So you have like training the model. This training function is doing nothing but just memorizing informations. All right, and then you have another functions that called predictions. So you just feed in test images, and then you want the model to predict a label for that. All right. So what it does is that it just comparing the test image with all the images in the training set, because it already memorized everything. So it's just comparing one by one, and then give you a predictions of the most similar image within the data set, and then just give you the label of that most similar training image. So that's what it does. Okay, that's it. What it does, a nearest neighbor. So, but how? So after it memorizing, and then we want it to predict, right? We said that it's give the most similar image. So how can we measure the similarity between the image and the test image, the training image and the test image, right? So the way that we are measuring the similarity between images is we call a distance matrix, all right? So there are several metrics that we can use, right? The first one we call the L1s, or Manhattan's distance, or we call a Manhattan distance, right? So it's just the absolute difference between the training and testing image. So what we are going to do by using L1 distance to compare two images, we just perform the pixel-wise absolute difference between the pixel-wise within the image itself. So we have the test image here. These are the number here is the pixel value of each pixel within the test image. So we subtract that pixel value using a training image pixel value, and then take the absolute of that. And then we're gonna get the pixel-wise absolute difference over here. And then we sum them all up, and then we're gonna get a single number, right? We're gonna get a single number, and then we keep doing this with all the training image, and then select the smallest number, which means that they are very similar in terms of pixel value. So that's the first distance matrix that we can use, right, for the nearest neighbor. So if you're going to write the script or the programs to perform a nearest neighbor classifier. This is the code, right? This is just pretty much all you need. It just, it's very simple, right? It has just two functions. So you can fit everything in a single slide. So these are the code that we can use to perform the nearest neighbor classifier. So we have these train functions, which is memorizing all the training data, and then when it's come to the prediction, you just loop through all the training image with the testing image that you want, and then just trying to find the minimum distance amongst all pair of testing and training image, and then you're gonna get the label of that testing set. So that's it for the nearest neighbor classification. That's what it does. It like essentially that's what it does. Okay. So the question is, with n examples, how fast is the training? Without looking at the slide. All right. So with n example, let's say that we have 10,000 images as a training data. That's n example. So how fast is the training? How fast is this one?
ON,
I'm sorry?
how fast? I mean the time,
Yeah,
right?
the time complexity. How fast is it?
ON, O,
ON?
no, O, what do you call? OHN, I think.
O hat N? What is O hat N?
Shit. Now come. Let me think.
So how fast can we train this model? Let's say that we have n example, n training example. How fast we can train this?
Ensemble, O.
So it would
O1.
be O1, right? It's
Yeah.
constant time because it does nothing but just remembering, going through all the training number, or just like one by one. So one image. So it's constant time. It's the O1. All right. So what within examples, how fast is the testing?
Training.
Yeah,
Testing.
how fast is testing? So how fast can we when we want to perform a predictions, how fast it can do?
This loop O. So N
Mhm.
time. ON. ON.
ON. Yeah, it's ON, right? It's linear time. So
Yeah.
yeah. So this is if you look at this time complexity, this is bad, right? We cannot afford the slow training time, but we need we can afford the slow training time, right? We can wait to train the model, but when we deploy the models in productions, we cannot afford that, right? We cannot afford the ONs. We need a fast testing, right? So probably this nearest neighbor classifier might not be a good choice. But if you have a situation need to use this one, yeah, just be aware that as your data set grow, the time that you need in testing time or inference time, that what we call inference time, will be increased linearly. All right. So we can say that a nearest neighbor classifier might be work well if you have a small size data set. But as your size of data sets or number of images or number of sample keep increasing bigger and bigger, so the testing time will go bigger and bigger as well. So just keep in mind that if you are going to use, or if you are in a situation that you need a nearest neighbor classifier, just be aware that the inference time may be high. Yeah.
Question.
Yeah.
Uh, on the choice of the K, the less K, I mean 1 or 3, and the more K is 11, 15, or even 15. So I think that this is hyperparameters, right?
Yeah.
It depends on the data sets. You need to try and see what is the best parameter. But I think if we choose small numbers, so it can be fast calculation, but the accuracy we don't know, right?
Yeah, we will talk later about that k nearest neighbor, but now we are talking about the nearest neighbor, which by default k is equal to 1, right? So yeah, we'll talk about how we are going to select the case, how it affect the performance of the model, something like that. But
Okay.
for now, just let's keep k is equal to 1 for simplicity. All right. So this nearest neighbor, um, so there are as you can see that the nearest neighbor, the testing time of the nearest neighbor classifier is quite high. It goes up linearly with your training data set. But there are many methods that we probably can use for fast approximations or the approximate nearest neighbor. There's a certain algorithm that we can do to speed up this process. So if you are interested, or if you are in need to use nearest neighbor classifier, you might probably need to look at a Facebook research that they try to optimize this process. Instead of ON, we can perform some approximations so that the testing time is reduced. All right, you can have a look at that, how they implement the optimizations of nearest neighbor. So if you look at the nearest neighbor, how it looked like, for example, this on the right side here is our training sample, right? And on the left side here is our testing sample. If we input this image, so then it will try to look through all the image within our training data set and then compare it and then see which one give the smallest absolute value of the distance, so that it will pick that as the class of our testing example. So if you look closely here, since the nearest neighbor, it used the pixel-wise absolute difference. So what it does is nothing but just use the pixel brightness value to subtract from each others, right? So as you can see, there are many of them that get the wrong categories because of that. So for example, this fork, sometimes it looks like a cat, sometimes it looks like a fork itself, or sometimes it looks like a car, for example. So this is how nearest neighbor works itself, right? So another thing that we might need to talk about in nearest neighbor is the decision boundaries, right? For example, if we plot the two dimensions of the x0 here is the value of pixel, one pixel, the other one would be another value of another pixel, right? The pixel value x0 and x1. So the nearest, this is the image of nearest neighbor in two dimensions, right? Each point here is the training example. So we give a label for each training example. So the different color belong to different uh, class or categories of the sample. So as you can see, for example, if we have a testing image and then it fault at this X area, so we can assume that this image would probably belong to the class or to the color red color group here. So as you can see here, the decision boundary is the boundary that can separate between the two regions, separate them apart, right? And sometimes the decision boundary can be very noisy, right? So for example, at the boundary between the blue and the red over here, it kind of like joggle around, right? So it's kind of so we can say that this probably be affected by some noise or some outlier. And for example, the yellow sample over here, like it's happened to be in the middle of the green categories. So this would probably be some noisy sample or some outlier. So the question is how can we smooth out these decision boundaries, right? So the answer is you just need more sample, right? You just add more sample or use more neighbors, all right? So that's bring us to the k nearest neighbor, all right? So if we use k is equal to 1, this is might be probably the decision boundary that we get. But if we keep k to 3, so we probably get a better area, right? Better decision boundary. So this yellow area now there's no yellow area now if we increasing the k, right, the number of closest points here, right? But we end up, so as you can see here, we get a much smoother boundary between different classes, right? So, as we increase the number of neighbors, we can get a better smooth boundary between classes, and then sometimes we can reduce the effects of the outliers or the noise, for example, the yellow area over here, right? But sometimes it uh, so as you can see here, it reduced the outliers if we increase the number of k. So yeah. And but when k greater than 1, there can be a tight boundary between the classes. So we some sort needing something to break this tight area over here. So we might come up with some sort of criteria that if any sample fall under this white area, we might need some sort of extra criteria or extra rules to break this tight area between the classes. Okay. Oops. And for the distance matrix, we already discussed about the L1 distance, right? So another distance that we can use is the L2, or sometimes we call it the Euclidean distance, right? So the difference between these two distance would be something like this, right? L1, if you go back to physics class, L1 is nothing but a distance, but L2 is nothing but a displacement. All right, so that's the difference. Okay, so this is the green one is what we call a displacement, which is L2, or sometimes you might have heard it. Some people call Euclidean distance. So yeah, if you compare to physics, it's called displacement. Okay, so that's the difference between the two distance.
In Vietnam, we call the busway.
Busway.
Birth.
But okay, I see.
Busway.
Yeah. So so if we compare the like using different distance matrix, we probably end up with some sort of different boundary between the classes. For example, if you look at this example and then we use the L1 distance, you can see that the boundary mostly can be either along with the x directions and y directions, or some sort of degree, right? Some sort of certain degree. And if we are using the Euclidean distance, we can see that it can cope with many angles, or it can smooth out the decision boundaries over here. All right, as you can see the difference, right? So it's either vertical or horizontal lines, or like 45 degrees, something like that. But if you are using the L2 distance, it can go like in many angles between that one. Okay, so but anyway, it depends on the types of data you have. So you might need to choose between either one of these and then see. You might need to try either one of this and then see whether which one work best for you. So if I can show you this is the simulations or the demos of how we can like choosing the k nearest neighbor, how it works, something like that, right? For example, if we choose L1 with let's say 5 classes, and then we have 50 samples, something like that. So this is what probably we end up with the boundary area if we are using k is equal to 1. If we are increasing k, so the decision boundary might probably look something like this. And also if we increase the number of neighbors, so the boundary area some sort of changing, right? As we increase the number of that, it keeps changing. So, and we can also move points somewhere around. If we move some point, so the boundary area would probably change accordingly. All right, for example, something like that. Right. So if you move this green area here, so this green now is kind of isolated from its original class. So this probably would be seen as the outlier or the noise, right? So you can play around with this one to try to see with different metrics. If you use L2, you're gonna get a better like curvatures for the boundary area. But using L1, you probably only get either horizontal, vertical, or 45-degree boundary area. Yeah. Right. So that's some sort of that thing. Yeah. You can try to play around with this one. Yeah, something like that. All right, so when we're talking about k nearest neighbor, so there's a k, right? So that's what we call a hyperparameters that we can choose or we can change, we can vary that value so that we can find the best value to our data set. So the question is, what is the best value for k to use, and then what is the best distance matrix to use, either L1 or L2. So what is the criteria to choose this one? So these two examples are what we call the hyperparameters. Like it's either the k or either the k or the distance matrix. So the choice of this one that we are using is it's very on your problems, right? It's very problem dependent. So we need to try trial and errors. So that's the only thing that we can do, right? There is no rules, there is no formulations, there is no equation. It's just trial and errors and then see the result, because it depends on the problem. So we cannot have a fixed rule. We cannot have the rule of thumb for that, for this particular kind of classifier. It just needs to trial and errors to see whether what work best for your data, for your task. All right. So in order to train the classifier and like how to choose the parameters, the idea would be you just training or choosing the hyperparameters. The first idea would be you are choosing the hyperparameter that work based on the entire data set. All right. You are just training your models on the entire data set, and then keep changing the hyperparameters k and the distance matrix, keep changing for your entire data set. All right. So that's one way you can do, but that's a bad that's a bad idea, right? Because the k is equal to 1 will always work perfectly on your training data set. Right. So this is a bad idea of how you train your models and choosing the hyperparameters. So never do this. All right. Training the models on your entire data set. All right. And the second idea would be split data set into training and testing, and then you choose your hyperparameter that work based on your test data. So that's the another idea that we can do, splitting out probably 70-30, 80-20% of those as the training and testing sample, and then train your models on your data set, but choosing your hyperparameters based on the performance of the models on test set. All right. So this is also a bad idea because because we have no ideas how the algorithm gonna works on the new data set. The new data, which means that when we train the models here, we keep trying and we keep changing the hyperparameters on training data set. But when we are going to choose which hyperparameter, like which distance matrix we're gonna use, and then which number of K we are going to pick for our models to deploy, we are choosing based on the test set. So this is the bad idea because we never know that how it is going to work on the data that it never seen before. All right. So for K nearest neighbor, this is a bad idea. All right. So the next idea would be you split the data set into 3 different data set. That is training, validation, and testing, right? And then you train your models and test the models on the validation set, and then you evaluate your models on the test set. But you choose the hyperparameters of the models based on the validation data set. All right, so this is a better idea. So the test set is going to be used once. All right, it's going to be used once, but in the training, we are training the models, keep changing the hyperparameters, and also testing or validating the hyperparameter at the same time while we're training. But when we are going to choose what is the number of K, what is the distance matrix, we are choosing based on these validations. All right, and then after that, we can deploy our models and test it once with the test model to see how it works. Yeah. And another idea would be using what we call a cross validations training. That is, we split a data set into a chunk, or we call a fold. So for example, here we have the 4-fold chunk, and then we take the first 3 as a training and the last one as validations. And then we keep shuffling this 4 for training the model and validation the models. And then we also testing a model once. And then we just choose the model that is work based on this you just calculate the average value among these shuffling models. All right, among these shufflings, and then you calculate the average over the result of that, which one is working best among this one, and then you select hyperparameter based on that, right? And unfortunately, this idea it is useful for a small data set, but when you are going to deep learning, right, you probably have a very huge data set. Training with this style using a cross validation might not be the best solution because it will require a lot of computational resources to use this one. So basically, in a large data set with deep learning, we basically back to the idea, the third idea. All right, you split the data set into a 3 set: training, validations, and the test set, and then you just train your models on this, validate it, and then test it once with the test set. All right. So this is just to show you that if you're using a cross validations and then trying different value of K using a 5-fold cross validations, this is what the accuracy that you can get. You just keep changing the K, and then checking the accuracy of that. For example, the each dot here is the each dot along x-axis here. It is represent the accuracy of the same k, but different fold, right? So for example, here we have 5-fold. At this probably, for example, 5k is equal to 5, k is equal to 7 around this area. And then we have a 5-fold cross validation, which means that we keep shuffling the fold as a validations. So the accuracy here, we're gonna get 5 dots, right? Because we perform that 5 times. We keep shuffling the fold so that we're gonna get this accuracy 5 dots. And then we take the line over here, it just at the middle or the average of each of accuracy of each k. All right, it just so what we see from here is it seems like that is working best for this data set is probably like 7, something like that. The highest one somewhere around here. All right. And the k nearest neighbor, we can see it as a universal approximations as well. So the number of training example affect the performance of the k nearest neighbor. So as we can see here, the training point, the black dot over here is our training point. And then if we train these models, if we train this k nearest neighbor, the true function, which means the function that is really represent this dot is the blue one. But if we train the k nearest neighbor with 5 training point, this might be probably the approximation of the function that we can extract by using k nearest neighbor. But if we increase the number of training point, we might get a better approximations of these functions. So if we keep increasing from 5, 10, 20, and 100, so the k nearest neighbor can approximate the value, can closely or nearly approximates the true value. So which means what the key takeaway here is that the number of training point affect the performance of the k nearest neighbor classifier. So as you increase the number of training sample, the k nearest neighbor will work better and better. Okay. And another property that we might have to be aware of is the problem with k nearest neighbor is we call the curse of dimensionality, which means that if we want the k nearest neighbor to approximate some functions, so the numbers of sample that is requires for the k nearest neighbor to do better at that data set would be the exponentials of that data set. All right, the exponential of the dimensions of that data set. For example, if the dimensions of the data set is just 1, it's required 4 points to approximate. For example, here, if you want to approximate these true functions, right? If we want to approximate these true functions, and then we this point, the features or the dimensions of the sample is just 1 dimension, we probably require only 4 points is enough. But if we increase the dimensions of the sample of the sample, we probably need the exponential, which is 4 to the power 2. So we require 16 sample. If our sample has 2 dimensions, we require probably 16 sample for the models to work to fit with that true function. So if we increase the dimensions of the sample to 3, so we need probably 4 to the power 3 or 4 cube of that. So that's many numbers of sample that we need so that our models or classifier can approximate that true functions, right? So if we think about the image, all right, if you think about the image, so just take the binary image. So the binary image at each pixel, it has only two values, right? 0 and 1. And then if we have the binary image of 32 by 32, all right. So the number of images that is required to train this k-nearest neighbor to fit the space of binary images would be 10 to the power of 308. All right. So if you compare this with the number of particles in this universe, so the possibility that is much higher than all the particle within the in this universe. So what we can say here, sometimes it's impossible to do so. All right. And the k-nearest neighbor, it is not very often used on the raw pixel for the classification, because first it's very slow at the test time. All right. And distance matrix on the pixel is not very informative. If you look at these three images, right, they're having the same L2 distance. If we compare the original image with each of these three images on the right, they are having the same L2 distance. All right, because using k-nearest neighbor on raw pixel, we just subtracting the image, the pixel value, right? So so that, which means that we are not getting much information about this one by using the k-nearest on raw pixel, right? However, the nearest neighbor work very well with the convolutional neural network features. So if you are going to use the k-nearest neighbor as a classifier, so you might not probably use it with the raw pixel. So you pass your image into a convolutional networks, and then you're gonna get a feature vectors. And, all right, and then you use those feature vectors to you feed that feature vectors into a nearest neighbor to compare with the training sample. So that's gonna work very well. All right, so when we talk about the deep learning or convolutional layers, we will see that how can we extract feature vectors and then use that to compute the nearest neighbor, or use a nearest neighbor classifier to classify the image. All right. Any questions about k-nearest neighbors or nearest neighbor classifier before we move on to the linear classifier?
So, which means that in a pictures, we should have many item to do the binary, I mean, classification. Let's say we classify dog, cat, and things. And then with the new image in, and we try to inference by on a KNN model, it's going to be try to map the pixel. They calculate the L2, let's say L2, and then come up with the numbers, and then they will compare to depend on which cluster, right? Based on the pixel only. But they base only one channel of pixel, or three channel, if a meme image or grayscale.
It depends on your image. If you have color, so it will compute pixel wise on each channels and then combine them together.
Okay.
So you compute the difference on red, green, and blue channels, and then you sum each channel up, and then you sum all them up again. Yeah.
Okay.
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 All right. So that's the first classical machine learning classifier. So the next one will be a linear classifier, right? So a linear classifier it used very often in neural network structures. All right. So when we talk about the neural networks, so we will often see a linear classifier as a part of that. All right. If you look at the neural network as a Lego stacking of things, stacking of layers. So linear layers will always be part of the neural networks. So for example, here we have a neural network of these classifications models, and then we will often see the linear layers at the end of each neural network, all right, of each models. So linear layers is quite important because it's part of the neural network architectures. Always, mostly, not always. Some of them not used, but mostly, I would say 80% that we have linear layers on neural network. All right. So yeah, to train the image classification using a linear model, we probably have to use a bigger data set and then more variety of image, more variations. So we can use CIFAR10, which is have the resolutions of 32 by 32 by 3, right? And if we look at the linear classifier in terms of parametric approach, so we can say that we have a training data X and a label Y, and then we have some sort of learning algorithm, right? We have some sort of learning algorithm, and then it can output the label, or it can predict us something. So we can look at this in terms of parametric approach, that if we feed in some X, which is some features, and then we have some sort of learning algorithms or the models that is learning about these features, and then it is trying to predict or estimate a Y, which is a labels of that particular features. So how can we represent this learning, or how can we represent this hypothesis in terms of parametric approach? Right. So here, if we have the image, the array of 32 by 32 by 3, that's the number, right? Number of pixels. So we have a total of 3072 numbers in totals, all right? And then we feed these numbers, so we can say that at a features, and then we can feed it into a functions of f, function f, which is a function f of x and w, all right? And this w, this is what we call a learnable or a parameters or a weight. Okay, so you will see that this w is a learnable parameters or weight, and then it will predict. Let's say that if we are using a CIFAR10, there are 10 classes, right? So it will give us predictions or a score of 10 number for each class, right? So if we look at in terms of a linear classifier, we can construct these functions as a matrix multiplication, which is linearly a matrix multiplications of the W, which is a matrix, multiply with the X, which is the value of this image. All right, it is a vector, which is a vector or feature vectors of the image. So we multiply the matrix with the vectors, so then we can calculate the score for each functions, so that we can represent a function of the function f of x w as the multiplications of matrix w and a feature vector x. All right. So if we take this as an example, right? If we take this as an example, so the matrix W can have a dimensions of 10 by 3072, all right, 10, which is equal to number of classes, and 3072 is equal to the dimensions of the image, all right, is the total number of pixels in our image. and the x will be a feature vectors. All right, x is a feature vectors, which is 3072. So we multiply these two, and we will get the output of 10 numbers, which is a score of each class. All right. So what we are doing here, some of you might wonder why do we get 3000? So we just multiply these dimensions of the image. So which means that instead of taking the square, we are stretching out the image into a vector, right? So because this image, if you look at this image, the original form of this image would be this 32 by 32, and then it has three channels, right? It has three channels over here. It has three channels. 1, 2, 3, right? It has three channels over here. So we just stretch this out as a vector. So we stretch it out as a vector of 1 by 372. All right. Instead of looking it as a cube, we spread it out as a column vectors. All right. So that's why we get a feature vector over here as the 3072 pixel. All right. And sometime we might probably want to add some bias. So we just add another value into this linear models. So if you look at these equations, it will look very similar like a linear equations, right? So it will look similar to mx plus b, right? So this is a linear models, right? Linear equations. I hope that's a basic, right? So yeah, so that's why it's called a linear classifier, because it's linearly multiply this value together, right? So if you take this image as an example, let's say that we have only like size of input image of 2 by 2, right? Of 2 by 2, and then we stretch pixel into a column vectors. So this is what we end up with. So it dimensions a vectors of dimension 4. All right, we stretch it out. And then we have a matrix W, which has the dimensions of 3 by 4. All right, three row and 4 columns. 3 row and 4 columns. And we have a bias term over here as well. So what we did is that we are multiplying this matrix with this vector. Right? We multiply this matrix with a vectors, with a feature vectors here, and then add the bias for each term. So this is what we call a score. So we got a score for each class. Let's say that we have 3 classes of cat, dog, and sheep, for example. All right. So the size, the number of row here will be equal to the number of class. All right. The number of columns here will be equal to the size, the total size of these feature vectors. All right. And the bias, the bias term is just a vector that is equal to the number of classes. All right. And then this is the score of each classes that after we perform these matrix vector multiplications and then add the bias term. And this is what we call a score. All right. So so this is how we can do the linear classifier. But if we look at it in another perspective, that is the algebraic viewpoint. So we can look at it like we can add this bias the way that we add bias term here. We can say that we can look at this operations in terms of algebraic viewpoint, because it's just performing the algebra equations. All right, so it's just the way we look at it. Yeah. And so we can add, so we're looking at, by looking at that in terms of algebra, so we can, instead of having one operations, addition operation here, we can move this bias term into this matrix, and then perform the multiplications, matrix multiplications, matrix and vector multiplication. So to do that, we just need to add another terms in our feature vectors. Just add one. That's it. Okay. So this is how we can look at it in terms of algebraic equations. All right. So this is what we call a bias trick. So instead of having another term over here, we just move it into we just combine it with the weight matrix. All right. It's just another way of doing, but this is not quite popular. Okay. When we are doing the deep learning or something like that, we are not doing that, but instead we are doing this as we are doing additional instead. All right. So so if we look at this linear classifier, the predictions also linear. All right, the predictions are also linear. So let's first ignore the bias. So if you scale the image, if you're doing something with the image, all right, if you're doing something with the image, for example, you multiply the image with some scalar value, all right, and then you can, the thing that you will get, it's just the scale version of that. All right. For example, if you are dividing each pixel of the image by half, which means that you reduce the brightness. So the final score of the prediction, we just one half of that, just divided by 2 as well. It's just a scale version of that. It's either scale up or scale down. All right. So which means that we are the classifier, the predictions of that is also linear. If you have a linear model, the predictions of that model also will be linear. All right. Whatever you did with input, it will be affect the output as well. All right. Whatever the scale you did with input, that scale will be also did with the prediction as well. All right, so that's what it is. Or we can instead of just stretching out the image, another way that we can do is that instead of turning this image into vectors, we might keep it as it is, right? We might keep it as it is, but we construct a weight to be the same size as our image. All right, the same size as our image. And then we perform a matrix multiplication between these two, add bias term separately, right? We can have, instead of one matrix W, we have 3 of them here. And then we multiply with this one, and we come up with the score for each class over here. So what it means here, it looks like we perform a template matching. Right, we have a template for each and every class here. So that this color represent one class, right? It's like we are having a template for each and every class, and then if we have an input, we just sliding this template over and see whether which one give the highest score, so that input image belong to that class, right? For example, if so, doing this way, we can visualize what exactly this weight matrix is doing, right? For example, we have this tree, so we can plot this out. We can visualize that what is this matrix represent. So for the plane, we might probably have a template that looks something very blue because it fly on the sky. And for example, for the car, we might have a mixture of like different shape of the car. And for the horse, we might have some sort of greens and the horse, something like that. All right. So a linear classifier, it has like one template per class. So we have a one template per class. So sometimes a single template cannot capture multiple mode of the data. So how do we what do we mean by that? If you look at this horse template, the template of the horse, you can see that there's this template, the horse has two heads. So which means that in our data set, we might have a horse that is probably turning to the left and then turning to the right. So when we are having one template for one class, the models might not be perfectly captured or might not be able to distinguish between different viewpoints of the horse heading left or horse heading right. So it might be confused sometimes with that one. All right, so which means that if you have a single template, we might not, the model might not capture multiple modes within our data. Okay. So if we are looking at the linear classifier in another viewpoint, which is the geometric viewpoint, so we can say that probably because it's linear, right? For each and every class, we are going to have the boundary, right? As a linear function, it depends on the equations that we can come up with or our model can come up with. So we can have the boundary draw to separate between different classes, right? So we can say that if after we perform multiplications and additions here, if the value falls somewhere along this line, it will be a car. If it falls somewhere around this line, it will be a cat. If it falls somewhere along this line, it will be an airplane, something like that. So this is how we can look at the linear classifier in terms of geometrics. So if you look at this in terms, if you have plotted in a higher space, so you will get a hyperplane that separate between each class, right? So that's what it means, that we can view this, or we can interpret the linear classifier in different viewpoints. Okay. So there's a hard case that linear classifier cannot perform. So these are the three examples that linear classifier cannot distinguish or cannot predict the class. For example, if we have the class one in the first and third quadrant, and then the second class on the second and fourth quadrant. So in this way, we will not be able to find the linear equations that separate between the two classes, right? And also with this sort of area which have a circle inside the circle blue inside a rectangle red. So linear models or linear classifier also cannot be classified in terms of this area. And as well as the third one that we have, that a circle in each quarter of that one. So yeah. So to summarize, we can build the linear classifier, or we can interpret the linear classifier in three different view, either algebraic viewpoint, visual viewpoint, or geometric viewpoint. It's just the way you look at it. Right? Also, like we mentioned in nearest neighbor, we need some sort of things to measure the performance of the models, right? So in linear classifier, we also have a score functions. So far we define a linear score function. Like we say that given the W, we can compute a class score for the image X, right? So we can compute the class score among other classes, and then we pick the one that had the highest score as the label of each image, right? So, but how can we actually choose a good W? All right, because the W is going to produce a score for us. All right. So the question, how can we actually choose what is the good value of W? So to measure whether what is a good value, or what is a good matrix W. So what we have to do is, first we have to use a loss function, right? We have to use what we call a loss function to quantify how good a value of W is. So we need a loss functions. And then we have to find the W that minimize the loss. All right, that we have to find that the W that minimize the loss functions. So what is the loss function itself? So the loss functions, what is the responsibility of loss function? So the loss function is nothing but it tells us how good is our model is currently, how good it is, right? That is the job of loss functions. So the low loss, which means our model is good. The high loss, which means it's bad. All right. So sometimes you might hear people say objective function, cost function, right? So they mean the same thing, okay? Objective functions, cost function, loss function, they mean the same thing. It can be used interchangeably between these two. And also sometimes we might have a negative loss function, or sometimes we call reward functions if you are working with the reinforcement learning. So they will call reward functions, or a profit functions, utility function, fitness function, something like that. So that's another name of the loss functions, but it just in the opposite meanings. So if it call objective functions or cost function, which means that we want to minimize it, right? If you see people using reward function, profit function, it negative of the loss, which means that we want to maximize it. All right. There's some case that you want to maximize value, and then in some cases you want to minimize the value. All right. So that's why it comes with the difference name, right? So now let's define something. So we are given a data set. So we can in our data set we have a data itself, which is labeled xi, along with it label which is yi. All right. So the xi is nothing but an image, and then yi it's just a label. It can be integer. Or it can be like the categorical data, like a dog, a cat, something like that. So it can be a number of 0, 1, 2, 3, 4, 5 to represent the class. All right. And then we have a loss for a single example. So we calculate a loss of the predicted value versus the true value of what we call a ground truth. Right. So that's how we calculate a loss function. So the loss functions for the data set, for the whole data set, is the average of the per sample losses. All right. So let's say that we have 50,000 images in our training sample, and then we feed this into the linear classifier. So for each and every image, we calculate the loss for each of them, and then we average all of those loss so that we will get a loss of the total data set. All right. So that's how we calculate the loss. So how to represent a class label, right? As I mentioned, we can represent a class label. So X is obviously the image. So a class label, you can label it as the characters, like fish, grizzly, something like that. Or you can represent it with the integer 1, 2, 3, 4, 5, something like that. Or you can represent the labels of each class by using what we call a one-hot vectors. All right. What is a one-hot vectors? So one-hot vectors, it's just one in one positions and zero elsewhere. All right. So that's what we call one-hot vectors. For example, if in our data set, we have 3 classes, so that we specify 0, 1 here, and the rest will be 0, which means this is belong to class 1. And then if we move 1 to here and the rest is 0, this is mean another class. All right, so what we mean by one hot is just we have a single one value in the vector. So this is a vector, right? So and then we have one in one single positions in the vector. All right, so that's what we call one hot vectors. So if we go mathematically, how this one hot vector end up with something like this? How can we convert this label into one hot vectors? So what we can do is that, for example, let's say that we have only 3 classes, right? So this is number 1, number 2, number 3. If we convert this decimal value, right? So this is what we call decimal. If you convert this decimal value into a binary representations, so this is the binary representations of decimal 1, right? So you can do 2 to the power 0, to the power 1, to the power 2, right? I hope you know. So let me just give you a quick example. So 1 in a decimal is equal to 2 to the power 0 multiply 1 plus 2 to the power 1 multiply 1 over here plus 2 to the power 2 multiply 1. Okay, so this 1 and 1 will be represented by this value. So which means that we have 2 to the power 1 here. You got by 2 to the power 0 multiply this with 1 plus this multiply with 0 multiply with 0. So if you sum this all up, it's equal to 1. All right, so that's how you convert from decimal to binary. All right, and this is 1 because you multiply this with 0, you multiply this with 1, you multiply it with 0. So this will end up with 0, this will end up with 2, this will end up 0. So you sum them all up, this will be equal to 2 in decimal. So that's how you convert the decimal into a binary. You got the idea, right? So that's how you convert this decimal to a vectors into binary.
Okay, clear.
Okay. Right. So that's how you do the one hot vector, or this how you can label your training data. Okay. So I think let's take 10 minutes break, and then we'll come back how we can train the models, how can we calculate a loss value for the linear classifiers, right? So let's just come back at 10:40, right?
Okay.
Dr. Joseph,
I guess.
you are not living in Thailand?
Yeah, I'm living in Thailand.
Oh, okay.
Mhm. I'm currently in Thailand. All right, let's come back and get started. So now we are going to discuss about how exactly the linear classifier model. So up until now, we already knows that how can we label the data, right, for linear classifiers, and then what is the loss functions? What is the roles of the loss functions in linear classifier, and then we already knows that how exactly can we view or how exactly can we interpret a linear classifier, right? For example, here we can look at it from different viewpoint, right? So now we are going to start at like seeing how exactly the linear classifier model works. All right, so this is how we can label the data. So we have a data set. We can prepare our data set in which the training data set have the image along with its label. So we can label it differently. It depends on your preference, right? And so so now we are going to talk about how exactly how it works. How can we choose a good matrix W, which is what we call a parameters, a learnable parameters, or the weight of the models, right? Suppose we have this 3 training example and then 3 classes, and then with some W's. So the score function will be this is the equations of the linear classifier, right? As we can see. So as I mentioned, or the loss functions, it is telling us how good our current classifier is, right? So the loss function is just the loss functions or the loss over the data set, the entire data set. It is nothing but the average of the loss over each example, right? So that's the loss function we have. And the first loss functions that I want to talk about is the multi-class SVM, which is support vector machines, right? So how is the support vector machine works? How it looks like? So this is a form of loss function for each example, all right? So for each example, let me just do this first. All right. So here's the loss function, the loss for each. So now we are going to discuss about multi-class support vector machine. Okay. So this is how can we calculate the loss for each example I, right? For each example I. So the loss value for each for that example I will be equal to 0 if the score functions of the correct class is greater than other class plus 1. All right, so the loss value will be 0. So what does that mean? What does that mean? Let's look at this example, this column. We feed in the car image, and then the score of the car is 4.9. All right. If we look at other classes, all right, if you look at other classes, we can see that the score of the correct class is yi. The score of correct class is greater than others classes, which is class J. This is also J. All right. So if you sum this up, if you sum these two up, you will get 3.3, right? And then plus 1, you get 4.3. It obviously less than 4.9, all right, which means that the score of this correct class is greater than the sum of score of other class plus 1. So which means that the loss value of this example will be equal to 0. So here our objective is that we want to minimize the loss value, which means 0 is good. 0 is good. Okay. Otherwise, if it's not equal to 0, it will be equal to the sum of this not incorrect class minus a score of the correct class plus 1, right? So that will be the class of that, the loss of that. So for example, if this is the image of the cat value, so the score of this image, the loss functions of this image will be what? 3, what is it? The sum of this, so you're gonna get 3.4, right? 3.4 minus this will be 3 minus this one, you will get 0.2 plus 1. So you get 1.2 as a loss function of this image. All right. So that's how the loss function is being calculated. So we can simplify this as a max between zeros and the score of the incorrect class minus score of the correct class plus 1. So take max of that. So you will get a loss for each example. All right. This is the SVM loss. So if you look, if we can interpreting the multi-class SVM loss as follow, for example, so we can see that if we plot the graph, right? If we plot the graph, the score of the correct class will be 0 if it is greater than the highest score of other classes with some margin. So right, so the score of the correct class will be 0 if it is greater than the highest score among other classes plus some margin. So the margin here can be any numbers. So in this example, we said the margin will be equal to 1. Okay, so then if the loss value of this correct class will be increasing as the as the value is less than this margin. So if you multiply, if you added the highest score of other class plus margin, and then it falls somewhere around here, so the loss function will be increasing, right? So here's the example, right? Like I did before. So here's the example for the first images you feed in. So you're gonna get a total of 2.9. So you take the max of 5.1 minus 3.2 plus 1. Okay, and then you plus the max of other class. So Sj is the other class. Okay, the other class would be minus 1.7 minus the score of the correct class, which is cat, right? 3.2 plus 1. And then you sum them all up, you're gonna get 2.9. That's the loss functions of this image. That's the loss value of that image. All right. And then for the next image, you feed this image into the linear classifier. So you compute the first one, the cat. So you take a max between 0 and 1.3 minus 4.9 and plus 1. So this term you're gonna get 0, right? So this term, this is gonna be going to oops, sorry. So this term going to negative, right? Is this term going to negative? So which means max of this one will be 0. And then this term is going to, oh no, different, it's wrong. It has to go back. I'm doing, all right. We are doing this for this image, the car image, right? So this term is going negative, all right? So max of this will be 0, comparing with this one, all right? And then for this term, this one, so this also going to negative, all right? Going to be negative. And then max of this will be 0. So you're gonna get 0 with this one. So if you look at that one, which means that the score of the car, which is the correct class, is higher than the other two, which means that the model get correct predictions. All right, so the loss value will be 0 for that. Okay. So next, if you compute the loss for this image, so you pass this image into the linear models, and then it gives you this score for each class, right? So you taking a max between 0, you're computing for this one, so you're gonna get going to some high value 6.3 here. All right, max between 0 and 6.3, you get 6.3. And then max between 0 and this term, you're gonna get 6.6, right? So you sum them all up, you're gonna get 12.9. So this is very high, right? So which means that what you can interpret with this one, so it give a very low score to the correct class. So which means that the linear models or linear classifier didn't do well with this image because the loss will be quite high. Okay. So then next, what you're going to do is that you sum them all up, and then you divide it by 3 in the number of class. So this will represent the loss over the whole data set. All right. So this is each image, each individual pixel, each individual example. All right. And then if you want to calculate for all the image in the data set, so you sum them all up, divided by the number of classes. So you're gonna get the average or the loss over the full data set. All right. So yeah, that's simple as that. So suppose that we have found so the reason why we are doing that, calculating the loss value, is that we want to find what is a good set of W, right? So that's the objective, right? We want to find a good set of W because this score is coming from this equation, right? Coming from this equation is coming from the matrix W multiply with a feature vectors of the image. So the reason why we are doing this is that we are finding what is the good value of matrix W. So that is our objective, right? We want to optimize this one. So suppose we found some W with loss is equal to 0. So the question is it unique? Is there any set of W that can give us the loss function, the loss value is 0, right? The question is, it's not unique, right? It's not unique. What we can do is that we can, if we have, so let's say that this is our set of W, is our set of W 0.1, 0.5, 0.7, 0.9. Let's say this is the set of W, right? This is our W that give us a loss equal to 0. All right. So the question is it unique? Like any other set of this value that also give us a loss equal to 0? The question is that the answer is not unique. So we can simply multiply this with any number, right? Any number, or we can scale it into 2. So we multiply this into this number, each number, and then we perform the Wx again. We will simply get loss is equal to 0 also. All right. So because it's just a scale versions of that. So why it is matter? So for example, right? So if we recalculating for this one, if we recalculating this is original W, and then this is using the 2W. All right, we probably end up with this loss function which give us the 0 loss value as well. All right. So how should we choose between W or 2W if they both perform the same, if they give us the same performance on the training data set? How can we choose between the two? We should choose W, or we choose 2W, right? So that's the question, because it's not unique, right? Yeah. So that's why it brings us to the term regularizations, right? It brings us to the term regularizations. So if you look at the loss functions here, so this is what we call a data loss, which means that the model prediction should match a training example. And then we add another term we call a regularization. It means that we want to prevent a models from doing too well, right? From doing too well on the training data set. That's what the responsibility of regularizations. So we add this term, which is the plus lambda of function, some function R, right? So the lambda is another hyperparameters that we can set, all right? So for example, the regularizations that we can add would be the L2 or L1 regularizations, or a more complex when we are talking about the convolutional neural network, we would talk about dropout batch normalizations, something like that. So the purpose of regularization is there are three purposes. So the first one, we add this regularization to express our preference to the model that we want something, all right, from the model. We want to express our preference in the models that we want something beyond just minimize errors, all right. So basically, when we train the models, we want to minimize errors. But sometimes it doesn't, there are many set of W, or there are many set of coefficient parameters that can give us the lowest loss value. So to distinguish that one, or to get a unique set of weight, we add a regularizations for this to express our preference, what kind of model that we want, right? And also to add a regularization is to avoid overfitting, right? To avoid overfitting. So that's one of the very important problems in deep learning or machine learning, which is overfitting, all right? So we add regularization for that. And also the third purpose would be to improve the optimizations, right? So when we are talking about the convolutional neural network, something like that, when we use some sort of function to that one, we might probably add some curvature into the space of the models, so that it get better models, right? For example, we can add the regularization to express our preference. So let's say that we have these two W, we have these two W, right? And then we multiply this W, each one of them, to this X, which is our input, right? We probably end up with the same number. We end up with the same number, which is the W1 multiplied with X and W2 multiplied with X. You get the same value, which is 1. All right. So but if you look at this, if you look at the elements or the value inside each W here, you can see that the W1, the model is just paying attention to one features within the image, because it's 1 over here and then 0 on the rest. So if we choose this model, which means that we want the model to pay attention to one particular features of the image or within our dataset. But if we choose this W2, which means that we want to spread out the weight. We want the model to look at every features within the image. All right, so that's what it means, so that we can add this some sort of regularization to tell the models that we want something like this. All right, we don't want you to look at just one features, but look at other feature as well. Right, so that's why. So different regularization would probably give you different way of expressions your preference over the models. So, and also the regularizations, we can use regularization to tell the models that we need a simple models, right? We need a simple model. For example, we have this four dot, right? And then we want to find the models. We want to find a model that represent this data set, right? That fit to this data set. But if the model F1 it fit perfectly, the model F1 fit perfectly with the data, but model F2 has a training errors, but it's simple. Like if you want to write this, F1, it would be a very complex equation, right? It would be a complex equations of this one. It would be some polynomial regression, something like that. It would be, for example, this model would represent the x squared plus x plus 10, something like that. So this is the equations of this blue model. But the F2 will be simple, will be just mx plus b, right? So it is just a linear model. So the linear model is much simpler than the polynomial models, right? So we can use the regularization to control that, even though there's errors in the training, but we can be okay with that. But give me a simple models. Don't give me a complex model, even though it fit perfectly with the data. So that's another purpose of regularizations, right? So that's the multi-class SVM loss, right? So the second loss that I want to introduce, it's called cross entropy loss, or multinomial logistic regressions. All right. So for SVM, we got the score, right? We got the score, the number. But for the cross entropy loss, we want to interpret raw score as a probability. All right. We want to interpret the score as a probability. So here's the equations of the softmax functions. It's just the functions of exponential. All right. So if we pass this image into our linear classifiers, and then we want to use a cross entropy loss, what we get is that what we are going to do is that first, the model will give us a score. This is the score. So that's what we can use to calculate the multi-class SVM loss. But instead of doing that, we want to interpret the score as a probability. What we have to do is that first, so this is what we call the unnormalized log probability, the raw score, or we call logits. All right. When we go to the convolutional neural network, you will heard this term very often, logic. All right. Just remember, the logit is the unnormalized log probability, or it is a raw score that the model give you, so that you plug this into the exponential functions. All right, you plug that in. So what you will get the unnormalized probability. You will get the unnormalized probability. You can see that the probability, in terms of probability, every number has to be greater than 0. All right. Right, probably has to be positive, 0 or positive, right? So as you can see, the frog has score of minus 1.7. Now it turned to 0.18 after you pass this value into this exponential value. So which is this term, right? Which is this term. You pass it. All right, and then what we are going to do next is we are going to normalize it. We are going to normalize it, right? This is the term that we are using to normalize. This is normalizations. All right, so finally, after you normalize it, you will get the probabilities. You will get the probability that telling you whether how confident the models is confident that the input image will belong to which class. Okay, so the probability that if the model give us will sum up, if you sum everything, you sum up to 1. So what we can interpret from here is that the model is 80% is 80% confidence that this image, this input image is a car. And it is 13% confidence that this input image is a cat. All right, so the probability just tell you the confidence of the models. So if you take log of that, you're gonna get you're gonna get the loss functions, the loss value. You just take log of this probability. So this is what we call a maximum likelihood estimation. So we're not going into detail, but this is how it called. You take a log of probability, and that's what you got a loss of that example. All right. So you got this probability, and then you have a ground truth, right? You have a ground truth. So a ground truth of this would be a cat. So the ground truth is that you want a models to predict this image as a cat. So it has to has a probability equal to 1 because that's 100%. All right. So this is the correct class of what we call a ground truth. So we compare the predicted probability with the ground truth, right? We compare them together. So the way you can compare this, you can use what we call the KL divergence. So the KL divergence is just the way you compare two probability, okay? Or another way you can use is the cross entropy. All right, the cross entropy, that's another way of comparing the two probability. All right, cross entropy is also include the KL divergence as well. So that's why we are using a cross entropy to do that. It's just the way that you compare two probability. All right, so after you compare these two probability, then you'll finally come up with some value of the loss functions, of the loss value, how it is deviate from the ground truth. All right, so that's what it tells you. Let's look at some example, right? So you feed in this image into your linear models, right? And then it gives you some sort of the score functions, or that's what a log probability, right? It gives you this raw function. And then this is your ground truth, because your ground truth is that the crayfish has to have probability is equal to 1. All right. And then you calculate, you compare these two value. You compare these two value. And then you will get the cross entropy loss. So what you can interpret is that you can interpret as that how much there are difference between the predicted one and the ground truth. So that's where you ask the model that how much better you could have done. Because, for example, this is the probability of 1, and this probably let's say 70%, right? So our objective is that we want to push the confidence of our models. If we pass this image, it has to predict, it has to give a confidence as close as to 100. So that's what we want, right? So if it is predicted that it's confident that 70% that this image will be crayfish, so the loss function is the gap to tell the model that you are 30% away from the correct answers. Can you do better? Can you push 70 to 80 to 90, something like that? So that's what the loss function tell the models. All right, this is another example. For example, here the grizzly bear, right? The Zelamont, it predicted iguana or something like that. So it's wrongly predicted. So the difference between the predicted value, the predicted probability, and the ground truth probability is quite high. All right. So which means that the model has to try to come up with a set of W so that it can do better. Right. So if we compare these two losses functions, right? So let's take some example of this. Let's assume that we have the image of the model will predict 3 classes, right? The model will predict 3 classes. And then this is the score of each each image. So the ground truth will be 0. So which means that if the model predict the score of the first element higher than the other, which means that's correct. All right. If what is the cross entropy loss and what is the SVM loss for these 3 samples? So so if you look roughly at this one, so the mode or the image, the model predict correctly, right? The model predict every image correctly. So this one is one image. This one is one image. This one is one image. This one is one image, right? Image 1, image 2, image 3. So these are all class 0, which is the ground truth y equals to 0, right? Which is represent corresponding to these positions. So if you look at this one, the model correctly predict every image, So what is the cross entropy loss and what is the value SVM loss for this set of image?
0.
Which one is 0?
Let me think.
Everything?
On SVM is 0.
What about cross entropy?
Cross entropy, because you have to normalize. Let me calculate by the exponential of the negative number. How much is it?
Yeah, just probably you can guess it. So
it should be all sum to 1. No, because this one is all sum to 1. So
yeah.
something.
So yeah, the SVM loss will be 0, right? Because it's all correctly predicted, and the cross entropy loss will be greater than 0, right? Because it's not that much difference from here. So yeah, it will be greater than 0, the cross entropy loss, because there's some mistake over here, because this is very close prediction, right, between the correct and incorrect class. So what happened to each loss if I slightly change the score of the last data point here? All right, for example, the cross entropy loss will change, right? If I slightly change the score of the last point over here, but the SVM loss will stay the same. So let's say that I increase this to 20. I increase this to anyway, let me see. So what happened if I double the score of the correct class from 10 to 20? So that the answer is the cross entropy loss will be decreased because the correct class has a higher probability, right? It will get higher probability. So the cross entropy loss will decrease because the model has more confidence. So that's why the cross entropy loss will be decreased. And the SVM loss will still 0 because it correctly predict everything. All right, so that's how it works. So finally, we have to construct the image classification. So we have some set of data, so we call data set, which is a pair of X and Y, image and labels. And then we have a score functions, we have a loss functions, right? And then we can train the models to loop over, to learn, to extract some features from the image. And then the question is how do we find the best W? Right? How do we find the best W? So we still have this question. We haven't yet answered the question how do we find the best W yet. All right. We just know how to measure the performance of the models. All right. We just know how to measure by using different loss functions, by using regularizations. We just know how we can quantify the performance of the model by using loss function. But we are not yet answered the question, how do we find the best W? All right. So next class, we are going to see the way how can we find the base W. So either we should choose between the W or 2W. All right, so next class we will see that, right? So any questions?
No, very clearly.
Okay. All right. If no questions, I think hands-on lab will give you a better idea of how it works, how everything works. So I will hand it over to Yi.
It's okay.
Okay.
Can you see the screen, everyone?
Yeah.
Oh, okay. I already updated the lab 7, which include the machine learning for classification that Dr. Chesat already covered in the morning. We will go through the KNN models and linear classifier. Okay, you can go to the Colab link here to download and copy to your drive. We can also do this on your local as well, but here I'm doing in the Colab for you to see. Okay, this have some the objective of this lab is that we firstly we will try to generate the data set. We context with the synthetic data set, and our goal is that we want to generate the two-dimensional synthetic data, which means that we have like two features of the data set. Okay, we can also work in this is the cipher data set that is kind of very popular for the image. If you know, I will share later. And we can implement, after that we will implement the KNN and linear classifier from scratch for you to look at. And I will go through how we can use the scikit-learn to apply both classifier to the dataset. Okay. So to use that, we need to import some libraries. This is kind of similar to you. That's in NumPy, and this is for visualization. And for the computer vision as well as deep learning, we often use the library Torch. This is for the tensor. Have you used the Torch library in NLP courses?
No, not yet.
Not yet. Oh, okay. Okay. In this one, we will try to use the symbol Torch for you to see, and we use the scikit-learn dataset. I guess that you are very familiar with this one in the machine in the computer program course, right? It can help us to do to employ some models. Okay. Now, as firstly, we will try to generate and visualize some synthetic data points. We have the library to create a data set that is from Mac classification. And we can actually do from scratch by using NumPy as well, by you can generate the data. And in this case, the number of samples is 200, and the number of features is 2. Number of class is 2. So can you guess that what is the size of the X? Sorry, let me run this first. What is the size of the X here?
Say 200 rows.
Yes.
So 202 features. So 202, I think.
Yes, right. Correct. Let's just share 200 by 2. So we have like the tables would have 200 rows and 2 columns that stand for the number of the features. And we also have the data of Y, right? Let's see, also have 200 rows and 1 column. That is the labels have the data set of the Y column, and we can also have the class, and that is the value is in the Y. So here is that we would like to check the unique value in the Y column, and we can see that this is the function to check all the unique values in the Y training set. And I forgot to say this. This one is the train test split, right? We would like to split the data set into 2 sets, the training and the testing. We can call that is training and validation as well. It depends on your case. So this one we call that is test set. And normally we use the 20% of the data set. We use that for the testing set. We can check the size as well here for the, let's see here to see. Sorry. Let's see 20% of this one. So we get 40 rows for the test, right? Here we check the unique lattice, and we see that in the Y training synthesis data, we have 2 unique values, 0 and 1. And that is the same for a unique value of test set as well. So have the 0 and 1. So this function is basically just check that whether that the unique trend lattice and unique test lattice is equal or not. So if we can run this one well, which means that it's that's equal to each other. This here is where we want to check the first row of the data, right? This is the first row, the first feature, the second feature, and the value of the Y. This is label 0. Now let's see how the data. Okay, this is scatter plot to show all of the data points. Here we will have, this is the training, right? So we have 200 points. No, I guess 160 points of the data, of the training data. And we use the color here to see that for the blue, it should be the 1 or the 0, and blue and red, which means that 0 and 1. So because our data sets just have 2 dimensions, so that's why we can visualize it in the 2D plane here. That is for visualization of the testing data set. The same. So now we move to the KNN. I guess that you know all of the background of the KNN already, so I move on. KNN, we have this already in the library of scikit-learn, but in this one, we would like to have the custom KNN classifier for you to see. And we can have we need to choose the K, right? So in this case, we choose the K default is equal to 3. We can flexible to change the K, but in this one we default to equal to 3. We create the last here for using to use in the NumPy, or we use in our CPU. I also create another last for the K9 classifier if you want to use it by the torch function, by the torch tensor. So let's run this already, and depend on our usage we use. Okay. In this case, if we don't say anything, which means that we use k equal to 3, right? So in this case, we want to use k equal to 5. And this one, which means that we would like to fit the training data in the model to train. And after the model already trained by the training data, we have the train model KNN here, and we use this model to predict the test data. And we can predict the Y. Okay, and now we can see the accuracy score, which means that, okay, let me show it first. KNN. Do you remember what is 15 means?
True positive.
Yeah. And this one with this is we have the two labels, right? The 0 and the 1. So this one means that is the predicted one. We predicted is 0 and actual is 0 as well, right? And 17 means that we predict the actual is 1, and we also predict the model predicted that is 1. So the accuracy means that we we let 15 we add bonus to 17 divided to sum of this table, right? So we got 80%. That is the meaning of accuracy. I'm trying to write it for you to see in the confusion matrix. Yeah, actual 0, predicted 0. And what the like machine learning model they want to do is they try to predict as much as possible. They try to minimize this number 4 and 4. They want to the number here is less as possible. And the best scenario that it will be like become 0 if we want, because we don't want to have any error. So this one is the error. Okay. We plot it here, right? And we also want, after the model retrained, we want to set the boundary to separate them together. So here. This is where they can help us to separate two classes in visualization. Okay. Now we move to the data set of Cypher. So this is where we want to check that our device is using CUDA or not. So in this Colab, we can have some option for the GPU, because GPU is necessary if you want to work with image. Let's check. Yes, it's one. CUDA. This is the table for us to see that how many GPUs that this machine is using, and this one is the first GPU, and this 0 is the name. So if we call this device the CUDA 0, okay. This can help us to know that whether the machine is using GPU or not. The number of GPUs that we are using is 1. Okay, now we are we want to download the Cypher data. For those who don't know this, the Cypher data is this is the Cypher 10 data set, because they say cipher 10 because it have the 10, and in the lecture we already see we can download the data directly from here, or um, we can use this function to download the data. When we download the data, we usually use the data loader, and we can set it by true if we want to download it, or we use false if it's downloaded already. I guess that I downloaded this already, so let me connect with the drive. So normally when we have the data loader, what in it is also we need to have the transformation. This is one have to transfer the data to the tensor, and this have to normalize the data. Normalize the data, which means that we need to define two things. The first is the mean, and the second one is the standard deviation. What is the outcome of when we normalize with mean 0 and standard deviation is 1?
Normal distribution?
No.
No.
Good guess.
This I mean 0. Standard to 1.
Okay. The value of that is can be like if we have the x and we normalize by mean 0 and standard deviation is 1, is the like x minus mean divided to the standard deviation, which means that the outcome not change. So it's just for the sample for you to see how we can normalize the data. So in this case we don't change anything. Okay. We define the transform first, and we let it here to see that what we want, how we want to transform the data. Let me run this.
All right, so I just want to add something here. So in machine learnings or in deep learnings, when you prepare your data set, all right, when you prepare your data set, what you have to do, one of the things that you have to do is what we call normalize your data, all right? So in terms of data science, when you're working with some data, there's a way that you normalize or standardize your data is to normalize it or to standardize it, all right? So which means that if you have the image that have a very wide range of pixel value, so you want to normalize them so that they are in the same scale. All right, they are in the same scale. So that's why you normalize the data first. Otherwise, your data will be jumping around. The value of data will be jumping around. If you plot it out, so the way you normalize it, you just divide it. You divided every pixel value by the means of all the pixel value in your data set. Right? And then you just add the standard deviations in your data set. So then now every pixel value in your data set will have the same scale. All right, it will be in the same scale. So that's why you're normalized. So it is one of the important step you have to do. Otherwise your model will not be able to converge or to generalize to the data. So normalizations and to normalize your data is very important. So it's bring your data to the same scale. All right.
Question. Actually, the image is scaled 0 to 255 already. So everything is should on one scale already, I think. I mean, the normalization in the machine learning, when let's say we have a salary and the one feature is age. So we normally we do the standard deviation, standard scalar, right? But for image, normally they have 3 channel, and we have the pixel 0 to 255. So it's fixed scale, I think, already. So which technique, I mean, is still standard scalar is the right technique we apply, or we use other scalar like min max or whatever the scale. I think it should be better to do the more do the gradient and more conversion easily to
No,
find things.
no, it's not in the same scale, in the sense that some of the image maybe probably close tend to be in the red channel. Some of the image maybe probably tend to the green channel. Some of the image maybe probably they have higher value in different channels. So now we want to bring everything to, you mean normalize it, which means that you bring everything to the centers of the distributions, right? So probably your original data will be skewed to the left or skewed to the right. But if you normalize it, everything will be in under the normal curve, on a Gaussian curve. So that's how you so because some of many image maybe tend to be in the red channels, maybe some of them tend to be in the green channels. All right, so your data probably skew at one side of that one. But now when you normalize it, you bring everything to be under the normal curve.
Okay, so even it's skew in the channel.
Yeah, but the value of each pixel still from ranging from 0 to 255, but if it puts the value to the curve of normal, the value will change, but it's still in the scale from 0 to 255. All right. Okay.
Okay, thank you.
After a lot of data, we try to bring the length of the cipher train and cipher test here. Let me see. We will have the training data is the 50,000 images, and the test data have the 10,000 images here. We load the first cipher train here to see the train, to see the image and the label, and this is the fraud, right? Because we want to transfer the data of the image into the NumPy array to see. The reason why to transfer this because is because the image when we converting PyTorch tensor image to the NumPy array, and for displaying with like Matplotlib or OpenCV, so normally let's expect the channel last format, because when we load the image, the format is channel, height, and width, right? So when we want to use NumPy, we need to let the channel as the last one. So we move that one, and this one it have that to use the data in our CPU and transfer this to the NumPy. After that, we multiply to this number, because this one, the range value from 0 to 1, so we need to multiply to 255. And we also need to define the last. This is the 10 lashes of the cipher 10. Okay, let's look at the size of the image, because this is the RGB image. So here is the number of the channel, and this is the size of the image, like 32 by 32. This size, if we see that is really that actually have the 32 pixel, right, in the column and in the row as well. Okay, let's see the data set how it show in the image of 10 glasses. The reason why we want to transfer to the NumPy because we want to try to use it in the scikit-learn, right? So, and scikit-learn just support for the NumPy, right? We now would like to use the Cypher to train in the KNN, but you know the dataset is kind of very large, right? To train now, so that now I would like to do the subsampling from the dataset. This function helps us to choose the sample from the dataset, and now we only to 1000 for the sample to train. After we will use this function to have the train subset, and we want that the test data set we can use the same function, but the size we use is that it's just equal to 40% of the sample size here, which means that we have 1000 for the training and 400 for the test subset, and we get it in the train loader and test loader if the batch size is equal to the number of the sample size, and we solve for it before training. Here is that we need to flag the data or stretch the data set. For example, here before originally the set of the training data we have here 1000 is the number of the image, right? The second dimension is the number of the channel, and this one is the height, like you can imagine like the rows, and this is the column. This is the image, right? 32 by 32. And what we need to do is that we flatten the data set here. We flatten the data set, which means that if we have like imagine that's red, green, blue, right? The first layer here, the second layer green, and the blue. We need to convert it into, for example, it's just sorry, like 2 by 2, 3 by 3 here, and we convert it into the vector like this. Now we have 9 values, right? So we trying to do the same for the blue layer and the green layer. So we finally we have the vector kind of like this. Oh, sorry. So at the end, actually, what we have after all is that we will have three channel multiplied to 32, right? Because it helps us to have the data set. It look like the table that you normally see. Do you understand this point? Okay.
Yeah.
So that's why we would like to flag the data. And now we have like the data set look like 1000 rows and 2072 columns. It look like the data set that we normally use in the machine learning. Okay, now we let's try to use the CUDA to train the model. That's why originally in the previously we defined the Toscanel classifier and trained that. The accuracy means that when the predicted y equal to the test y, the actual value of y, and this is the accuracy. Now we try, in this case, the each trend out of the value of x and y is a tensor, right? If we want to transform it into the NumPy, we will use this one, GPU and NumPy. Let's do it again of this function, custom KNN classifier, and use the k equal to 3. We see some, actually it will have to show the same result here, 24% for the accuracy of the testing set. Okay, now you try to use the scikit-learn library for KNN as well. For this one, this is the KNN classifier of scikit-learn. And if we want to use the k equal to 3, we just set the number of neighbors equal to 3. And if you want to k equal to 5, just change this as the to define the hyperparameters for the KNN. And this is for the training, and this is for the prediction of the testing set. And like we showed before, for the cipher, we have 10 lattices. So the confusion matrix will show us 10 by 10, like 10 by 10 matrix. I will show it in this way for easier to see. So 24 is that there are 20, they are correct 24 for the plane lattices, right? So we try to maximize the number of this diagonal. Okay, now we also have the exercise here. You can download the Colab, the notebook, into your drive and do this. It's just basically you will have to generate the training data, training labels, and use the list of k, because this is the parameter we want to try to see that whether which case is the best for the prediction. And we look all of the steps and choose the k and show the result here. You should do this at home. Okay, now I move to the linear classifier. Okay, firstly, we define as like the KNN, we define the class custom perceptron for the linear classifier. Our class we have two class, 0 and 1. In this case, we will redefine the y. When equal to 2, we turn it to -1 and keep the 1 for the last one. And this step it helps us to, because we have the learning rate, right? So this is the learning process. And what we need to do is we want to update the ways to have the best W and best bias. We will try to minimize the loss function to have the best weights. And that is where how we can update the weights and the bias through this training process. And finally, we have the operations. Run this one. There are two hyperparameters here. We need to choose the learning rate and the number of iterations, which means that the number of steps of the training. We can increase or decrease this number, and this is also your experiment. You will try with some scenario to see how the results are. We also have the confusion matrix here. This is for existing data set, and the accuracy is 95%. Let me plot here to see the boundary. Because this is the linear, actually we only have two features, and the linear here is look like the linear line in the 2D dimension, right? So it's almost that is kind of the straight line to separate two lashes. That is two lashes. Now we would like to handle multiple lashes. The number of lashes can be not only 2, but can be 3, 4, 5, or even 10 like the cipher 10. The weight here is like the matrix that show in the lecture. And do you remember the size, the weight here? Okay. If the S we have the size is m by n. No, let it like if the S like number of rows n by d, right? So the weight is channel by d, right? So what we need to do is we need to dot product x and y transpose. So here we need to product this, and finally we will have the y is kind of n by c. So we have 3 columns of the channel, and after that we use the argmax function to choose which one is the maximum, so we can choose that last as the final result. So by the axis one. Do you understand this point?
Yes.
Yeah.
Yeah, clear.
This will take time for the strand, I guess, but can be done soon because we already sample the data set. We don't use the whole training.
How many data you sampled? 1,000?
Yes, 1,000 for the
Okay.
training and 400 for the. In waiting time, we can take a look at this one. This is also for the scikit-learn implementation. Oh, okay, we got a result here. Multi-last perceptron accuracy is quite low, right? But this is how we just show you how we can use the custom last that we can design by ourselves based on the algorithm of the classifier, and we can have the result by ourselves, 28 something%. And in scikit-learn, the name of the model is logistic regression. I guess that you already tried this in the computer program, right? So you can use the same to see the confusion matrix. That's firstly, I use this one is for the synthetic data that we originally defined in the first line. And we can also use the scikit-learn for prediction. And as discussed in the beginning, because the data set we generate have the different range, and we don't know what is actually the range of the data set. So before training, we need to scale the features. And scikit-learn also support us to do the scaling process. And this is the standard scaler to have the data always in the range of mean is 0 and standard deviation is 1. So it can have to scale all of the feature of our data set. This is actually the synthetic data set. So we need to scale that first. And we fit that data, the training data, into the scaler. And then we also need to transform the x-test as well, because we want it on the same scale of the training set. And here is that we initialize and train the perceptron model to use the number of iteration 100. This is the learning rate. Okay. And this is the predict the test on the test data. Okay, finally, we also have one assignment for you to test for the KNN algorithm from SRAT. And you can also implement the symbol linear classifier use scikit-learn to build and evaluate the KNN and linear classifier and visualize for decision battery of both model. And the take home here, we need you to see that how the learning rate can control how much we can adjust the weights during each update. So in this experiment, you can see that the learning rate, if that's too small, the perceptron can not have the significant progress. And too class, maybe that can overshoot the optimal solution. So the action here, we want that we can do the experiment with different learning rate to see the optimal value. So in the first assignment, the parameters that we want you to test is that the list of the K, right? So here we also to define the same for the learning rates. You should define the learning rates like 0.01 and 0.02, let's say something like that. And we try with different learning rate to see how the training process work. And we need to, and here for the initialization of the weights, we need to ensure the weights in the bias are initialized properly, and typically with the small random values, because we not only define the learning rate, but we need to initial for the initial weights in the bias as well. And then after that, the training process can have to update the weights and the bias. So we want you to initialize that first properly and have to faster the training process. And after you can do that and then submit. This one you can also submit to the TU as well, Dr. Chasha.
Yeah, you can submit it too. I'll create a submission form.
Yeah, okay. I think that's all for the lab of KNN and linear classifier. Do you have any question?
I guess the best case is 3 or 5 and the learning rate is around 0.1. That's my experience.
Okay, based on your experience in the previous course, right?
Never know. Have to try
Yeah.
first.
No, below 0.1.
Yeah, different data set. That's what we need to do. I think what is the the most optimal one is not important than the way that we can have the multi parameters and know the way to see the how we can choose one of them as the optimal result. I think that's the important one to do. Okay, I think that's all.
All right. Thank you, Yi. So, any other questions?
No, clear.
Okay. So then, this week, just me wrap up, shortly wrap up. So this week we learn about the feature description, right? So we learn how to perform feature matchings, image stitchings, panorama, camera calibrations. So those are belong to the traditional based methods, computer vision methods, right? And then today we are moving to the learning based methods in which we learn the KNNs and linear classifier as a machine learning for image classifications, all right? So next week, we are going to dive deeper into the optimization process. For example, we still have to find a way how to choose the best optimal weight metrics that we have to do. So that's belong to the optimizations. And then next week we will dive deeper into a deep learning fundamental. For example, neural network, multi-layer perceptrons, how is the back propagations, how is the convolutional neural networks works. And also we'll start the object detections using like something like RCNN, something like that. So that's all about next week. And also on Saturday afternoon, we are going to have a mini project presentations. Okay, don't forget that. What you have to submit. So let me recap again. So what you have to submit first, your code from that template, right? And then second, the presentations telling what features you added to the apps, and then how are those features works, the algorithm, something like that. So explaining what you have done, okay, and then present to the class. So I think we have 9 people, right? 9 people. So we probably maybe 10 minutes each, 10 to 15 minutes each, okay, for each next week. All right. So any questions?
No, just figured out how to do the AR later with my dinosaur.
Okay. All right. So then if there's no further questions, I'll see you guys next week then. All right. So bye-bye. Have a good weekend.
Thank you.
Bye.
Bye-bye.
Thank you.
you,
Thank you, Yi.
Professor.
Bye-bye.
Goodbye. See
Thank
you.
you.
Have a good day.